Picture this. You're staring up at the night sky, billions of stars twinkling above you, and suddenly a profound question enters your mind. Where did all of this come from? What existed before the universe began? You're not alone in this curiosity. Throughout human history, we've gazed upward and wondered about our cosmic origins. The Big Bang Theory stands as our best scientific explanation for how our universe began. A spectacular moment approximately 13.8 billion years ago, when everything we know erupted from an infinitely dense, infinitely hot point, smaller than an atom. In that first fraction of a second, space itself expanded, matter formed, and the cosmic dance that would eventually lead to stars, planets, and ultimately us began. But here's where things get truly fascinating. When we ask what came before that moment, we're asking about something that might exist outside the very framework of our reality. It's like asking what's north of the North Pole. The question itself challenges our understanding of existence. Scientists, philosophers, and spiritual thinkers have all grappled with this profound mystery. Some suggest there was nothing before, that the Big Bang marked the absolute beginning of everything, including time itself. Others propose more exotic possibilities, previous universes, higher dimensions, or realities that operate under physics we can barely comprehend. What makes this question so compelling is that it sits at the intersection of science and philosophy. It pushes the boundaries of what we can observe, measure, and ultimately know. Our human minds evolved to understand the middle-scale world around us, to track animals, recognize faces, and navigate landscapes. We weren't designed to comprehend the beginning of time or the edge of infinity. Yet somehow, through mathematics, through powerful telescopes, and through thought experiments that stretch our imagination, we've managed to peer back almost to the very beginning. We've detected the faint afterglow of creation still reverberating through space, the cosmic microwave background radiation. We've unraveled how elements formed and how galaxies took shape. But those first moments, and what might have come before, remain shrouded in mystery. Consider for a moment how remarkable it is that we can even contemplate these questions. We are, in a very real sense, the universe becoming aware of itself. The atoms in your body were forged in the hearts of ancient stars. The capacity of your brain to ponder cosmic origins is itself a product of 14 billion years of cosmic evolution. When you wonder about what came before the Big Bang, you are part of the universe asking about its own birth. This is not just academic curiosity. These questions touch something deep within us, a yearning to understand our place in the cosmos, to grasp the full story of existence. Are we part of something larger, something cyclical, something that has happened before and will happen again? Or is our universe a singular miracle, a one-time emergence from nothingness? The answers we seek might be beyond our current scientific instruments, beyond our mathematical models, perhaps even beyond the capacity of the human mind to fully comprehend. But that doesn't mean we stop asking. With each new generation of telescopes, with each advancement in theoretical physics, we edge closer to understanding. As we journey through the cosmos tonight, we'll explore the frontiers of human knowledge and venture into realms where certainty gives way to possibility. We'll gaze into the deepest past of our universe and even dare to ask what might have existed before the very concept of before had any meaning. Imagine trying to describe colors to someone who has been blind from birth. In many ways, that's the challenge we face when trying to conceptualize what existed before the Big Bang. Our language, our intuition, and even our mathematics were developed within this universe, with its particular laws of physics and its linear flow of time. Attempting to describe a realm that might operate under entirely different principles is like trying to pour the ocean into a teacup. The concepts simply overflow our capacity to contain them. And yet, this hasn't stopped humanity from trying. From ancient creation myths that speak of cosmic eggs or primordial waters, to modern theories of quantum fluctuations and membrane collisions, we have always sought to push beyond the boundaries of the known. The mystery of what existed before the Big Bang has profound implications for how we understand ourselves and our place in reality. If the universe had a beginning, does that imply intention, design, or purpose? Or is our existence merely a statistical inevitability in an infinite cosmos? These questions have echoed through philosophy, religion, and now science. for as long as humans have contemplated their existence. As we explore this territory together, we'll encounter concepts that may seem alien or counterintuitive. We'll hear about quantum foam and vacuum fluctuations, about eternal inflation and cyclic universes. Some of these ideas come from the cutting edge of theoretical physics, while others blend into metaphysics and philosophy. All of them represent human attempts to peek behind the cosmic curtain, to glimpse what might have existed before time began. One particularly fascinating aspect of this quest is how it unites disparate fields of human inquiry. Particle physicists working with enormous accelerators find themselves contemplating questions once reserved for theologians. Cosmologists studying the large-scale structure of the universe encounter puzzles that philosophers have debated for millennia. Mathematicians developing abstract models suddenly find their work applicable to the most fundamental questions of existence. And perhaps most remarkably, these investigations often lead to practical technological advancements. The same theories that help us understand the first moments of the universe have applications in fields ranging from medicine to computing. When we push at the boundaries of knowledge, we never know what unexpected benefits might emerge. Tonight, we'll also confront the humbling reality that some questions may remain permanently beyond our grasp. There may be fundamental limits to what we can know about the origins of everything, but even if we never arrive at complete answers, the journey of discovery transforms us. Each generation builds upon the insights of those who came before, gradually expanding the sphere of human understanding. As we gaze up at the stars, we're looking back in time. The light from distant galaxies has traveled for millions or even billions of years to reach our eyes. In a very real sense, astronomy allows us to see into the past, but to see beyond the Big Bang, to glimpse what might have existed before our universe began, requires different tools altogether. The tools of mathematics, theoretical physics, and sometimes pure speculation. The history of science teaches us that today's speculation often becomes tomorrow's established theory. Ideas that once seemed radical, like continental drift, or the notion that time itself could stretch and contract, eventually gained acceptance as evidence accumulated and understanding deepened. Perhaps someday, the nature of what existed before the Big Bang will transition from mystery to knowledge. For now, though, we stand at the edge of understanding, peering into the cosmic dawn. The quest to understand what came before the beginning of time represents humanity at its most ambitious. Reaching beyond the known, stretching our minds to encompass realities larger than ourselves, and refusing to accept that any question is permanently unanswerable. As we continue our journey through cosmic history, we'll first establish what we do know with reasonable certainty about the Big Bang itself. We'll explore the evidence that supports this remarkable theory and examine exactly what it does and doesn't tell us about the birth of our universe. Only then can we begin to speculate with scientific rigor about what might have existed before time as we know it began. The Big Bang. These three simple words attempt to encapsulate the most extraordinary moment in cosmic history, the birth of everything we know. But what exactly do we mean when we talk about the Big Bang? It wasn't an explosion in space, as the name might suggest. It was an explosion of space itself, the sudden, rapid expansion of the very fabric of reality. 13.8 billion years ago, in a flash beyond human comprehension, our universe began its journey from a state of unimaginable density and temperature to the vast cosmos we observe today. To truly appreciate the Big Bang theory, we need to understand what it explains and what it doesn't. The theory describes with remarkable precision how our universe evolved from its earliest moments onward. It explains how primordial plasma cooled and condensed to form the first atoms. It accounts for the abundance of light elements like hydrogen and helium that we observe throughout the cosmos. It predicts the existence of the cosmic microwave background radiation, the afterglow of creation itself, still visible to our instruments as a faint hum permeating all of space. But the standard Big Bang theory doesn't explain the very beginning itself. It doesn't tell us what caused the Big Bang, or what, if anything, existed before it. As we trace the history of our universe backward in time, our mathematics leads us to what physicists call a singularity, a point of infinite density and infinite temperature, where the known laws of physics break down. It's as though reality itself hits a wall approximately 1 Planck time, about 10 to the negative 43 seconds, after the beginning. This singularity represents the limit of our understanding. Beyond this point, the equations that describe our universe cease to make sense. Space and time as we understand them may not have existed. The very concepts of before or earlier than may lose their meaning when we approach this boundary. Imagine trying to measure locations north of the North Pole. The concept simply doesn't apply once you've reached the pole itself. Similarly, asking what happened before the Big Bang might be a question without meaning if time itself began with the Big Bang. But this mathematical roadblock hasn't stopped scientists from developing theories about how the earliest moments of our universe unfolded. One of the most significant advancements in our understanding came with the theory of cosmic inflation, proposed by physicist Alan Guth in 1979. According to this theory, the universe underwent a period of exponential expansion just moments after the Big Bang. In a tiny fraction of a second, perhaps 10 to the negative 36 seconds, space expanded faster than the speed of light, stretching from subatomic scales to cosmic scales. This inflationary period helps explain several puzzling features of our universe. It explains why the cosmos appears remarkably uniform in all directions, even though opposite sides of the observable universe should never have been in contact with each other. Inflation accounts for this by proposing that all regions of our observable universe were once in close contact before being rapidly stretched apart. It also explains why space appears so flat rather than curved, and why we don't observe magnetic monopoles that should have been produced in abundance during the Big Bang. The concept of cosmic inflation dramatically changes our picture of the early universe. Before inflation theory, physicists struggled to explain how regions of space that appear identical in temperature could have achieved this uniformity when they were too far apart to have ever exchanged energy or information. Inflation solves this by suggesting that these regions were once much closer together, allowing them to reach thermal equilibrium before being stretched to opposite sides of the cosmos during the inflationary period. Similarly, measurements show that the geometry of our universe is remarkably flat. Parallel lines remain parallel, and the sum of angles in a triangle equals 180 degrees, even on cosmic scales. Without inflation, this flatness would require an almost impossibly precise balance of matter and energy in the early universe, a level of fine-tuning that seemed inexplicable. Inflation naturally produces this flatness by stretching any initial curvature, much as the surface of a balloon appears increasingly flat as the balloon expands. The evidence for inflation continues to grow. Subtle patterns in the cosmic microwave background radiation match predictions made by inflationary models. These patterns represent tiny quantum fluctuations that existed during the inflationary epoch, stretched to cosmic scales by the rapid expansion. These same fluctuations eventually grew through gravitational attraction to become the galaxies and galaxy clusters we see today, a direct connection between quantum physics at the smallest scales and the largest structures in our universe. After this brief but crucial inflationary period, the universe continued to expand, but at a decreasing rate. As space stretched and cooled, the fundamental forces of nature, gravity, the strong and weak nuclear forces, and electromagnetism separated from what may have been a single unified force. The cooling universe allowed quarks to combine into protons and neutrons, and eventually these particles formed the first atomic nuclei. For hundreds of thousands of years, the universe remained an opaque plasma of charged particles, with photons, particles of light, bouncing endlessly from one particle to another like pinballs in a cosmic machine. During these first minutes, the universe was a nuclear fusion reactor of unimaginable scale. The temperature and density were so extreme that atomic nuclei could form through the fusion of protons and neutrons. Hydrogen fused into helium, and trace amounts of lithium formed. This process, called Big Bang nucleosynthesis, lasted only about 20 minutes as the expanding universe rapidly cooled below the temperatures needed for nuclear fusion. The theory predicts that the resulting mix of elements should be roughly 75% hydrogen and 25% helium by mass, with just traces of lithium. Precisely what astronomers observe in the oldest stars and gas clouds, providing another powerful confirmation of the Big Bang model. Then, approximately 380,000 years after the Big Bang, a profound transition occurred. The universe had cooled enough for electrons to combine with nuclei, forming the first neutral atoms. Suddenly, photons could travel freely through space. This light, released when the universe became transparent, still travels through the cosmos today, stretched by the expansion of space to microwave wavelengths. We detect it as the cosmic microwave background radiation, a snapshot of the infant universe, and one of the strongest pieces of evidence for the Big Bang theory. This cosmic microwave background, discovered accidentally by Arno Penzias and Robert Wilson in 1965, appears as a nearly perfect thermal radiation with a temperature of just 2.7 Kelvin, almost but not quite absolute zero. The slight variations in temperature across this background, just 1 part in 100,000, reveal the seeds of cosmic structure. Regions slightly denser than average became the nurseries for galaxies, while less dense regions evolved into the vast cosmic voids that separate galactic superclusters. These temperature variations were mapped in unprecedented detail by satellites like COBE, WMAP, and Planck, giving us an actual image of the universe when it was less than 1% of its current age. No stars yet existed, and the universe consisted primarily of neutral hydrogen and helium gas, gradually clumping together under the influence of gravity. After perhaps 100 million years, the first stars ignited, their ultraviolet radiation beginning to reionize the surrounding gas. These first stars were likely very different from those we see today, enormously massive, intensely hot, and short-lived, containing only the primordial elements created in the Big Bang. As we look deeper into space with our telescopes, we're looking further back in time. The light from distant galaxies has traveled billions of years to reach us, showing us these galaxies as they were in the remote past. The farthest objects we can observe bring us to just a few 100 million years after the Big Bang, a time when the first stars and galaxies were forming from primordial gas clouds. But even our most powerful telescopes cannot directly observe the Big Bang itself or the inflationary period that followed. The James Webb Space Telescope, launched in December 2021, is designed to peer even further back, potentially glimpsing the very first galaxies as they formed. By detecting infrared light, Webb can see objects whose visible light has been stretched to longer wavelengths by the expansion of the universe. This phenomenon, known as redshift, is similar to how the pitch of an ambulance siren drops as it moves away from us. The greater the redshift, the more distant and therefore older the object appears to us. Webb may help us understand how the first galaxies assembled and evolved, filling in crucial details of our cosmic history. To probe these earliest moments, scientists must rely on particle accelerators like the Large Hadron Collider, which recreate, for the briefest instance, the extreme energies that existed shortly after the Big Bang. By smashing particles together at nearly the speed of light, physicists create miniature fireballs that mimic the conditions of the early universe. These experiments have confirmed many predictions of the Big Bang theory and continue to refine our understanding of cosmic origins. One triumph of these experiments was the discovery of the Higgs boson in 2012, a particle predicted by the Standard Model of particle physics. The Higgs gives mass to other elementary particles through its associated field that permeates all of space. In the extreme heat of the early universe, the Higgs field behaved differently, allowing particles to move at or near the speed of light. As the universe cooled, the field settled into its current state, giving particles the masses we observe today. This transition was a crucial step in the evolution from the plasma of the early universe to the structured cosmos we inhabit. The Big Bang theory isn't just a story about the past, it also tells us about the future. The same equations that describe the universe's birth and evolution also predict its fate. Current observations suggest that the cosmos will continue to expand at an accelerating rate, driven by a mysterious force scientists call dark energy. Galaxies will move farther apart, stars will burn out, and in the unimaginably distant future, even atoms may decompose. The universe born in fire may end in ice, a cold, dark expanse of emptiness, with all energy evenly distributed and no further work or change possible. This acceleration of cosmic expansion was one of the most shocking discoveries in modern cosmology. Until the late 1990s, Most physicists expected that the universe's expansion would be slowing due to the gravitational attraction of all matter. Instead, observations of distant supernovae revealed that the expansion is speeding up, as if the fabric of space itself contains some intrinsic energy that pushes galaxies apart with ever-increasing force. This dark energy makes up about 68% of the total energy content of the universe, yet its fundamental nature remains one of the biggest mysteries in physics. The remaining composition of our universe is equally puzzling. Ordinary matter, the stuff of stars, planets, and people, accounts for just 5% of the cosmic energy budget. Another 27% consists of dark matter, a substance that doesn't interact with light but makes its presence known through gravitational effects. We can see its influence in the rotation of galaxies, the bending of light around massive clusters, and the patterns of cosmic structure formation. Both dark matter and dark energy were present in the earliest moments of the Big Bang, shaping how our universe evolved from its fiery birth to the complex cosmos we see today. This narrative of cosmic evolution, from the Big Bang through star formation, planet building, the emergence of life, and possibly an eventual cold death, provides a scientific framework for understanding our place in the universe. We exist in a middle chapter of a story that began long before us and will continue long after. The atoms in our bodies were forged in stellar furnaces that exploded billions of years ago. We are, quite literally, made of stardust temporary arrangements of matter that became conscious and began to wonder about its own origins. But the Big Bang theory, impressive as it is, leaves open the fundamental question: what came before? If the universe began with the Big Bang, what caused this extraordinary event? Was there anything, any form of existence, any precursor state before our universe came into being? Some physicists suggest that asking what came before the Big Bang is meaningless if time itself began at that moment. In his famous book, A Brief History of Time, Stephen Hawking compared this to asking what lies north of the North Pole. The question itself assumes a framework that doesn't exist. Yet this philosophical stance, while logically consistent, fails to satisfy our deep curiosity about origins. It feels incomplete, like a story missing its first chapter. Others argue that the singularity at the beginning of the Big Bang isn't a physical reality, but a mathematical artifact, a sign that our theories are incomplete. Just as Newton's laws of motion break down at speeds approaching the speed of light, requiring Einstein's relativity to take over, so might our current understanding of physics break down under the extreme conditions of the Big Bang. Perhaps a more comprehensive theory, one that unites quantum mechanics with gravity, would remove the singularity and allow us to peer even further back in time, maybe even beyond the Big Bang itself. Before the Big Bang will follow a similar path from speculation to acceptance. For now, we stand at the edge of knowledge, with mathematics and physics as our guides, but imagination and wonder as our constant companions. The cosmos is vast beyond comprehension, ancient beyond reckoning, and still holds secrets we're just beginning to unravel. As we transition to exploring the concept of time itself and whether anything can exist without it, we carry with us this understanding of the Big Bang, not as an explosion in pre-existing space, but as the birth of space, time, and matter themselves. The question of what came before challenges not just our scientific knowledge, but our very conception of what before means when time itself may have a beginning. As we contemplate the profound question of what might have existed before the Big Bang, we encounter an even more fundamental puzzle. Can anything exist without time? This question has fascinated philosophers for millennia and now occupies the minds of theoretical physicists working at the very frontiers of human knowledge. It challenges our most basic intuitions about reality and forces us to reconsider what existence itself might mean. Time seems so fundamental to our experience that imagining reality without it stretches the limits of human comprehension. Every moment of our conscious lives unfolds within the flow of time. We remember the past, experience the present, and anticipate the future. The very language we use to describe existence is saturated with temporal concepts. How could anything exist without these fundamental aspects of reality? Yet modern physics has revealed that time may not be the absolute universal phenomenon we intuitively perceive it to be. This revolution in our understanding began with Albert Einstein's theories of relativity in the early 20th century. Before Einstein, physicists following Isaac Newton's framework viewed time as an absolute flowing at the same rate for everyone everywhere, completely independent of space. Time was seen as the cosmic clock, ticking steadily and uniformly throughout the universe. Einstein shattered this view with his special theory of relativity in 1905. He demonstrated that time does not flow at the same rate for all observers. It actually depends on their relative motion. Two observers moving at different speeds will experience time differently. For someone traveling near the speed of light, time passes more slowly than for someone at rest. This isn't an illusion or a problem with measuring devices, it's an actual difference in how time unfolds. Perhaps even more profoundly, Einstein's theory united time with space into a single entity, space-time. In this framework, time isn't separate from the three dimensions of space, but is instead the fourth dimension of a unified space-time continuum. Just as we can't separate length from width from height in a three-dimensional object, we can't truly separate time from space in the fabric of reality. Einstein further revolutionized our understanding with his general theory of relativity in 1916. This theory revealed that gravity isn't a force acting across space, as Newton had described it, but rather a curvature of space-time itself. Massive objects like stars and planets create dents or curves in the fabric of space-time, and this curvature guides the motion of other objects, creating what we perceive as gravitational attraction. Crucially, this theory showed that not only does motion affect time, but gravity does as well. Time passes more slowly in stronger gravitational fields, another deviation from our intuitive understanding of time as absolute and universal. These insights from relativity theory lead to fascinating questions about time at the boundary conditions of our universe. If time is intertwined with space, and if space itself began with the Big Bang, could time also have a beginning? And if so, what could it possibly mean for anything to exist before time? The very word before assumes a temporal relationship, one event preceding another in a sequence. Without time, such sequencing becomes meaningless. Some physicists suggest that time as we understand it did indeed begin with the Big Bang. In this view, asking what came before is like asking what's north of the North Pole. It's a question that mistakenly applies a concept beyond its domain of validity. Just as north loses meaning at the pole itself, before might lose meaning at the beginning of time. Others speculate that time as we experience it might be emergent, a property that arises under certain conditions rather than a fundamental feature of reality at all scales. Perhaps at the quantum level, or in the extreme conditions near the Big Bang, time operates differently, or may not exist in any recognizable form. Quantum mechanics already hints at this possibility with phenomena like entanglement, where particles appear to influence each other instantaneously across any distance, seemingly transcending our usual temporal constraints. The quantum realm presents its own profound challenges to our understanding of time. According to quantum mechanics, subatomic particles don't always have definite properties. We remember the past, but not the future. Eggs break and don't spontaneously reassemble. Coffee cools, but doesn't spontaneously heat up. This directionality is linked to the concept of entropy, the tendency of systems to move from ordered to disordered states. But some physicists wonder if entropy and time's arrow are fundamental or merely emergent properties that don't apply at the most basic levels of reality. The search for a theory of quantum gravity, a framework that would unite Einstein's relativity with quantum mechanics, has led to several fascinating approaches that further challenge our understanding of time. One of these is loop quantum gravity, which suggests that space-time itself isn't continuous but quantized, made up of discrete units at the Planck scale, approximately 10 to the negative 35 meters. In some versions of this theory, the Big Bang wasn't the beginning of time, but a bounce, a transition from a previous contracting phase to our current expanding one. Meanwhile, string theory and its more comprehensive extension, M-theory, propose that our universe may have 11 dimensions, with 7 of them curled up so tightly they're unobservable in our everyday experience. In this framework, time might be just one dimension among many, and what we perceive as the passage of time could be our limited perspective of a much richer dimensional reality. Another intriguing concept is timeless physics, advocated by physicist Julian Barber and others. This approach suggests that time doesn't flow at all. There is no passage of time in any fundamental sense. Instead, the universe consists of a vast collection of nows, complete configurations of the universe at an instant, with each now containing records, like memories or fossils, that create the illusion of past and future. In this view, time's flow is a psychological construct rather than a fundamental reality. These ideas may seem abstract or even incomprehensible, but they highlight a critical point. Our intuitive understanding of time, shaped by everyday human experience, may not apply to the universe at its most fundamental level or in its earliest moments. Might need to be reframed entirely if time itself isn't what we think it is. Let's consider a thought experiment to illustrate this challenge. Imagine a two-dimensional being living on the surface of a sphere. This flatlander has no concept of up or down. Only forward, backward, left, and right have meaning in their experience. If we tried to explain the concept of up to this being, we'd be introducing a dimension beyond their experiential framework. Similarly, when we try to conceive of existence before time, we may be attempting to apply a concept that only has meaning within our temporal framework to a domain where that framework doesn't apply. Some theoretical frameworks suggest that what we perceive as the beginning of time might actually be a boundary condition, not a beginning in the temporal sense, but a mathematical edge of our model. Physicist Stephen Hawking proposed the no-boundary proposal, along with James Hartle, suggesting that asking about time before the Big Bang is like asking about what's south of the South Pole. Just as the Earth's surface curves around smoothly at the pole, with no boundary, time might similarly have no sharp beginning, but rather curve smoothly, making the concept of before inapplicable. Alternatively, some models propose that time might extend infinitely into the past, with our Big Bang being just one event in an eternal sequence. In these scenarios, the singularity at the beginning of our observable universe doesn't represent the absolute beginning of time, but rather a state of maximum entropy or minimum information. A reset point where records of previous cosmic epochs become inaccessible to us. The challenge of understanding existence without time becomes even more profound when we consider consciousness. Our subjective experience seems inextricably linked to the flow of time. Our thoughts unfold sequentially. Our experiences accumulate in memory. Our sense of self persists through temporal change. Can we even conceive of consciousness or existence outside this temporal framework? Perhaps the closest analogy in human experience comes from certain meditative states or mystical experiences reported across cultures and throughout history. In these states, individuals sometimes describe experiencing a timeless awareness, a sense of being outside the flow of time, where past, present, and future seem to exist simultaneously, or where the very distinction between them dissolves. While these subjective reports don't constitute scientific evidence about the nature of reality, they suggest that human consciousness may have some capacity, however limited, to conceptualize existence outside our usual temporal framework. Philosophers have long grappled with these questions about time and existence. Parmenides, an ancient Greek philosopher, argued that change is merely an illusion and that reality is timeless and unchanging. Plato, influenced by Parmenides, saw the material world of change as less real than the eternal, unchanging world of forms or ideas. Augustine of Hippo struggled with the nature of time in his Confessions, famously remarking, "What then is time?" In more recent philosophical tradition, Immanuel Kant proposed that time isn't a feature of reality itself, but rather a structure imposed by the human mind to organize our experiences. According to Kant, we can't perceive or think about the world except through the lens of time, but this doesn't mean that time is an intrinsic property of reality, independent of our perception. These philosophical perspectives remind us that the question of time's nature isn't just a matter for physics, but touches on fundamentally philosophical issues about the relationship between mind and reality, between how things appear to us and how they might be in themselves. Modern physics has added empirical weight to these philosophical speculations. Experiments repeatedly confirm the predictions of relativity, that time dilates with motion and gravitational strength, that space and time are aspects of a unified spacetime. Quantum mechanics reveals a subatomic realm where particles can exist in superpositions of states and where cause and effect become blurred, These aren't just theoretical constructs, but have been verified through precise measurements and observations. The quest to understand time at its most fundamental level continues at the intersection of theoretical physics, cosmology, philosophy, and even cognitive science. Some approaches look to thermodynamics and information theory, exploring whether time's arrow emerges from statistical principles rather than being fundamental. Others investigate quantum gravity theories that might reveal how space-time itself emerges from more basic structures. As we ponder whether anything can exist without time, we should remember that our language and concepts evolved to describe middle-sized objects moving at moderate speeds in Earth's gravitational field. They may be inadequate for describing reality at its most fundamental level or in the extreme conditions of the early universe. The ultimate nature of time may be stranger and more profound than our everyday intuitions can grasp. This doesn't mean we should abandon the quest to understand. Throughout history, human imagination and mathematical creativity have repeatedly transcended the limitations of everyday intuition, developing frameworks that can describe aspects of reality far removed from direct experience. From the invisible world of atoms to the mind-bending implications of relativity, we've pushed the boundaries of comprehension. Perhaps someday we'll develop a framework that allows us to meaningfully conceptualize existence without time, or to understand time itself as emergent from something more fundamental. For now, the question of whether anything can exist without time remains one of the deepest mysteries at the frontier of human knowledge, a puzzle that spans physics, philosophy, and our very understanding of what it means to exist. As we continue our exploration of what might have existed before the Big Bang, we'll next consider a possibility that maintains a cyclical patterns have shaped our understanding of the world. The changing seasons, the waxing and waning of the moon, the daily cycle of sunrise and sunset, these recurring rhythms embedded themselves deeply in our ancestors' consciousness. Perhaps it's no surprise, then, that many ancient cultures conceived of time itself as cyclical rather than linear. From the Hindu concept of cosmic cycles spanning billions of years to the Mayan calendar with its interlocking temporal wheels, the idea that creation moves in great circles rather than straight lines has profound historical roots. Modern cosmology has revived this ancient intuition in a surprising way. What if our universe isn't a one-time event, but part of an endless cycle of expansion and contraction, of big bangs followed by big crunches, followed by new big bangs? This concept, known variously as the cyclic or oscillating universe theory, offers a compelling alternative to the idea that our universe appeared from nothing, with no preceding cause or antecedent state. The cyclic universe concept addresses one of the most profound philosophical challenges posed by the standard Big Bang theory, the problem of a beginning. If the universe began at a specific moment, what caused this beginning? And what, if anything, existed before? These questions seem to push beyond the boundaries of science into the realm of metaphysics or theology. A cyclic universe neatly sidesteps this conundrum by proposing that there was no absolute beginning, just an infinite series of cycles stretching endlessly into the past and future. The modern scientific version of the cyclic universe theory began taking shape in the 1920s and 30s, with physicists like Alexander Friedmann and Richard Tolman applying Einstein's equations of general relativity to the cosmos as a whole. They discovered that under certain conditions, a universe might expand for a time, then halt and reverse into a contracting phase, eventually collapsing back to a state of extreme density and temperature, only to bounce back and begin expanding again. This oscillating model gained significant attention in the mid-20th century as an alternative to the Big Bang theory. However, it faced serious challenges as observational evidence increasingly supported the Big Bang and as theoretical problems emerged. One fundamental issue concerned entropy, the measure of disorder in a system, which, according to the second law of thermodynamics, always increases over time. If entropy carries over from one cosmic cycle to the next, each successive cycle would be more disordered than the last, with longer expansion phases. Tracing this pattern backward in time would still lead to a beginning rather than an infinite past. The discovery in the 1990s that our universe's expansion is accelerating posed another serious challenge to the classic oscillating model. This appeared to rule out the possibility of a cyclical universe, at least in its traditional form, but theoretical physics is nothing if not ingenious. In the early 2000s, physicists Paul Steinhardt and Neil Turok proposed a new version of the cyclic universe based on concepts from string theory and M-theory frameworks that attempt to unify quantum mechanics and general relativity. Their model, sometimes called the ekpyrotic universe theory, from a Greek word referring to a cosmic fire, envisions our three-dimensional universe as a brane, short for membrane, floating in a higher dimensional space. In this scenario, our universe cycles through periods of expansion and contraction, not because of its own internal gravity, but through interactions with another brane. When these branes collide, an event that might happen once every trillion years or so, the energy released creates conditions similar to the Big Bang, initiating a new cycle of cosmic evolution. Importantly, this model doesn't require that the entire universe collapse back to a singularity, only that the distance between branes periodically decreases to zero. The ekpyrotic model addresses several challenges faced by earlier cyclic theories. It provides a mechanism for resetting entropy between cycles, solving the thermodynamic problem that plagued older oscillating models. It also accommodates the observed accelerating expansion of our universe, suggesting that this acceleration actually helps prepare conditions for the next cycle by clearing out matter and energy, creating a smooth template for the next collision. Another modern approach to cyclic cosmology comes from loop quantum cosmology, an offshoot of loop quantum gravity. This framework suggests that when matter becomes extremely dense, as in the final stages of a cosmic collapse, quantum gravitational effects create a repulsive force that prevents the formation of a singularity. Instead, the collapsing universe bounces back, beginning a new phase of expansion. This Big Bounce theory provides another mechanism by which one universe could give birth to another in an endless cycle. These theoretical frameworks remain speculative, existing at the frontier where mathematics and physics merge with philosophy. But they share a compelling vision that our universe may be one chapter in an endless cosmic story, one iteration of a pattern that has repeated itself, perhaps with variations, countless times before and will continue long after our particular cosmic epoch has ended. What evidence might support such a grand vision? While direct proof remains elusive, several observations and theoretical considerations lend credibility to cyclic models. For one, these models naturally explain the remarkably flat geometry of our universe without requiring the fine-tuned initial. This radiation could indicate that our universe remembers something of a previous cosmic epoch. Similarly, gravitational waves ripples in space-time, detected for the first time in 2015, might carry echoes of previous cycles if they manage to survive the transition from one cosmic epoch to another. If we could somehow prove that our universe is indeed cyclical, the implications would be profound. It would mean that the matter and energy that make up our bodies and our world have been recycled through countless cosmic iterations. The atoms in your hand may have been part of stars, planets, and perhaps even living creatures in previous cosmic epochs, a kind of physical immortality spanning trillions of years. The cyclic vision also transforms our understanding of cosmic time. Rather than a linear progression from a singular beginning to an eventual end, time becomes more like a spiral, returning periodically to similar states, but never exactly the same. Each cycle might have its own distinct characteristics, its own unique evolution of galaxies and stars, perhaps even its own forms of life. This conception of cosmic cycles raises fascinating philosophical questions. If the universe has cycled through infinite iterations in the past, has everything that could possibly happen already happened? Has some version of Earth, of human civilization, of you reading these words, existed in previous cycles? Or do the fundamental parameters, the laws of physics, the distribution of matter and energy, change from cycle to cycle, creating truly new possibilities each time? Some versions of cyclic cosmology suggest that each universe gives birth to a slightly different successor, with small variations in physical constants or initial conditions. Over vast timescales, this could create a kind of cosmic evolution, with universes becoming increasingly capable of complexity and perhaps even conscious life. In such a scenario, our universe's apparent fine-tuning for life might not be a coincidence or the work of a creator, but the result of a long evolutionary process spanning multiple cosmic cycles. The cyclic universe concept resonates with many religious and philosophical traditions and eras. Of course, the scientific versions of cyclic cosmology differ from these traditional conceptions in crucial ways. They're based on mathematical models and physical principles, rather than religious or metaphysical assertions. They make specific, potentially testable predictions, and they don't necessarily imply purpose or design in the cosmic process, though they don't exclude such possibilities either. Critics of cyclic universe theories point to several challenges these models still face. Some question whether entropy can truly be reset between cycles without violating established physical principles. Others note that any evidence from previous cycles would likely be erased during the extremely hot, dense phase of the transition, making empirical verification difficult or impossible. And some argue that cyclic models simply push the question of origins back a step. Even if our universe had predecessors, how did the whole cycle begin? Proponents respond that an infinite cycle has no beginning. It cycles all the way back, just as it cycles all the way forward. This concept of actual infinity in physical reality challenges our intuition, but has precedence in mathematical thinking. Alternatively, some suggest that the cycle itself might have emerged from quantum fluctuations in a pre-existing state, though this again raises the question of what that state was and where it came from. What makes the cyclic universe concept so compelling despite these challenges is its elegant symmetry and its resonance with patterns we observe throughout nature. From the water cycle to the carbon cycle, from the rotation of galaxies to the revolution of electrons, circular patterns pervade our universe at every scale. Perhaps the cosmos as a whole follows this same fundamental pattern, eternally renewing itself through an endless dance of expansion and contraction, creation and dissolution. The debate between linear and cyclical cosmologies reflects a deeper tension in human thought, between narratives with clear beginnings and endings, and those that emphasize eternal return and renewal. Both perspectives capture something important about our experience of reality. We witness irreversible changes and unique events, but also recurring patterns and regenerative processes. Perhaps the ultimate truth about cosmic time incorporates both these aspects in a way our current models only partially capture. As we've explored various models of the cyclic universe, we've remained within a framework that assumes our universe, or something like it, is all there is, cycling through time in a self-contained process. But what if our universe is not alone? What if it's one among many in a vast multiverse? This possibility opens yet another avenue for understanding what might have existed before the Big Bang, one that expands our perspective beyond even the grandest cycles to encompass a true infinity of cosmic possibilities. When we gaze up at the night sky, we see countless stars scattered across the darkness, each a sun, many with their own planets, forming a galaxy of hundreds of billions of stellar systems. Beyond our Milky Way lie billions more galaxies, stretching out to the limits of our observable universe. This cosmic vastness already humbles the human imagination. But what if even this immensity, our entire observable universe, with its estimated 2 trillion galaxies, is just a single bubble in an infinitely larger reality? What if our universe is merely one among countless others in what physicists call the multiverse? The concept of the multiverse represents one of the most profound expansions of our cosmic perspective since Copernicus displaced Earth from the center of the solar system. It suggests that our universe, everything we can observe, measure, or potentially interact with, may be just one region of a much vaster reality containing other universes with potentially different properties, histories, and even laws of physics. This idea challenges our definition of everything and offers intriguing possibilities for what might have existed before our Big Bang. Unlike the cyclic universe theories we explored previously, which propose that our universe is the latest in a temporal sequence of universes, the multiverse concept suggests a spatial expansion of reality, multiple universes existing alongside or parallel to our own, perhaps separated by dimensions we cannot directly perceive. In this framework, our Big Bang might not represent the beginning of everything, but rather the birth of our particular cosmic region within an eternally existing multiverse. The multiverse isn't a single theory, but rather a family of related concepts arising from different areas of theoretical physics. The most widely discussed version emerges from inflationary cosmology, the theory that our universe underwent an incredibly rapid expansion in its earliest moments. According to physicist Alan Guth and others who developed inflation theory, the process that caused our cosmos to inflate may be eternal, constantly creating new bubble universes in different regions of space. Within this energetic medium, small regions occasionally transition to a lower energy state through quantum fluctuations, creating bubbles that rapidly inflate to cosmic scales. Our universe would be one such bubble, but the inflationary process continues elsewhere, generating new bubbles, new universes, endlessly. If this model is correct, there could be infinitely many universes constantly coming into being across the vast expanse of the multiverse. In this picture, asking what existed before our universe becomes a matter of perspective. From inside our bubble universe, the Big Bang appears to be the beginning of time. But from the perspective of the larger multiverse, our Big Bang was simply one event among countless others in an eternal process. There was no before from our local time perspective, but the multiverse itself may have existed eternally. Another version of the multiverse emerges from string theory, which attempts to unify quantum mechanics and general relativity by proposing that the fundamental building blocks of reality are not point-like particles, but tiny, vibrating strings. The mathematics of string theory seems to require additional spatial dimensions beyond the three we experience, typically suggesting that reality has 10 or 11 dimensions in total, with the extra dimensions curled up so tightly we don't notice them in everyday life. One particularly intriguing development from string theory is the landscape concept, the idea that string theory doesn't predict a single unique reality, but rather allows for an astronomical number of different possible universes, each with different physical constants and laws. Some estimates suggest there could be 10 to the 500th power different possible configurations, a number so enormous it's practically infinite for all human purposes. Each location in this vast landscape of possibilities might correspond to a different universe with its own unique properties, different masses for elementary particles, different strengths of fundamental forces, different numbers of spatial dimensions that have expanded to macroscopic size. Our universe, with laws of physics that allow for complex structures like galaxies, stars, planets, and life, would be just one possible configuration among an almost inconceivable number of alternatives. A third approach to the multiverse comes from quantum mechanics itself. According to the many worlds interpretation proposed by physicist Hugh Everett in 1957, quantum events don't resolve to single definite outcomes as our everyday experience suggests. Instead, all possible outcomes occur, each in a different branch of reality, creating an ever-multiplying array of parallel universes. While initially considered a radical fringe idea, the many worlds interpretation has gained significant support among physicists and philosophers of science in recent decades. If the many worlds interpretation is correct, reality consists of an endlessly branching tree of alternate universes, each differing initially by just the outcome of a single quantum event, but with these differences compounding over time to create vastly different histories. In some branches, dinosaurs were never wiped out by an asteroid impact. In others, Earth never formed. In still others, the fundamental constants took different values during the early universe, leading to entirely different cosmic evolutions. Unlike the cosmological multiverse scenarios, the quantum multiverse doesn't necessarily address what came before our Big Bang. It's more concerned with what happens after universes begin. However, some theoretical approaches combine these perspectives, suggesting that quantum branching might apply to entire universes, potentially including their beginnings. A fourth multiverse concept comes from mathematician Roger Penrose's conformal cyclic cosmology. This model proposes that what we perceive as our universe's beginning and end are actually connected, forming a continuous cycle. Each iteration of the universe, each eon, begins with a Big Bang and ends with a maximally expanded state after all matter has either fallen into black holes or decayed into radiation. Penrose suggests that this maximally expanded empty state is physically equivalent to the compressed state of a new Big Bang, allowing the cycle to begin again. In Penrose's view, our universe would be just one eon in an infinite sequence, with each eon effectively constituting its own universe with its own space and time. This differs from other cyclic models in that it doesn't involve a contracting phase or bounce. Instead, it mathematically transforms the end of one universe directly into the beginning of another through conformal rescaling. What evidence might support these mind-bending multiverse theories? Direct observation of other universes would seem impossible by definition, since they exist outside our observable reality. However, some scenarios suggest that universes might interact in subtle ways, potentially leaving detectable signatures. For instance, if our universe literally collided with another bubble universe at some point in cosmic history, this collision might leave a detectable pattern in the cosmic microwave background radiation, the afterglow of the Big Bang that still permeates our universe. Several research teams have searched for such patterns, with controversial and so far inconclusive results. Another potential line of evidence comes from the apparent fine-tuning of physical constants in our universe. Constants like the strength of the electromagnetic force or the mass of the electron seem precisely calibrated to allow for the existence of stable atoms, stars, and ultimately life. If these values were even slightly different, our complex universe could not exist. This fine-tuning presents a puzzle. Why should these constants happen to have exactly the values needed for complexity? The multiverse offers one solution to this puzzle. If there are countless universes with different physical constants, it's not surprising that we find ourselves in one compatible with our existence. We simply couldn't exist in the vast majority of universes with different constants. This is an application of the anthropic principle, which notes that our observations of the universe are necessarily constrained by the conditions required for observers to exist. Critics argue that this anthropic reasoning isn't scientifically satisfying, as it seems to explain away fine-tuning rather than explaining it. But proponents point out that in a true multiverse scenario, the apparent fine-tuning of our universe requires no special explanation beyond the fact that different universes have different properties, and observers necessarily find themselves in universes compatible with their existence. The role of quantum mechanics in supporting multiverse theories deserves special attention. Quantum theory has repeatedly demonstrated that reality at the smallest scales behaves in ways that sharing information instantaneously across any distance. Empty space teems with virtual particles popping in and out of existence. These quantum phenomena, verified by countless experiments, suggest that reality is far stranger than our everyday experience indicates. The leap from these microscopic oddities to the possibility of multiple universes isn't as great as it might initially seem. If particles can exist in superpositions of states, why not entire universes? If virtual particles can emerge from the quantum vacuum, why not entire cosmic regions? The mathematics used to describe quantum fields naturally extends to cosmic scales in many multiverse theories. Quantum field theory, our most successful framework for understanding particles and forces, describes fields that permeate all of space. In inflationary multiverse scenarios, it's a quantum field, the inflaton, that drives the creation of new universe bubbles. The random fluctuations in this field, governed by quantum uncertainty, would determine where and when new universes form. If the multiverse exists, it dramatically reshapes our understanding of cosmic origins. The beginning of our local space-time would be just one event in an eternal process of universe creation, playing out across an unimaginably vast or infinite expanse. This perspective also transforms our understanding of cosmic fine-tuning and our place in reality. Rather than requiring our universe to be unique or specially designed with precisely the right properties for life, the multiverse suggests we're in a universe compatible with our existence simply because we couldn't exist in the countless others with different properties. Like organisms adapted to particular ecological niches, conscious observers would naturally find themselves in universes whose properties allow for their evolution. The philosophical implications of the multiverse are profound and far-reaching. If the multiverse contains an infinite number of universes with varying conditions, it might contain every possible configuration of matter and energy, including exact duplicates of our universe and ourselves. In an infinite multiverse, everything that can happen will happen, not just once, but infinitely many times. This concept challenges our notions of uniqueness and identity. If countless copies of you exist across the multiverse, each experiencing slightly different lives based on different choices or circumstances. What does that mean for concepts like individual destiny or the uniqueness of personal experience? Some philosophers argue that in a true multiverse, every possibility is actualized somewhere, effectively dissolving the distinction between what is merely possible and what is actual. Others point out that even in an infinite multiverse, each individual universe and each conscious observer within it would still experience reality from their unique perspective. The existence of other universes or other versions of ourselves wouldn't change the reality of our immediate experience or the significance of our choices within our local context. The multiverse also raises profound questions about the nature of scientific explanation. Traditional science seeks simple, elegant laws that account for complex phenomena. The multiverse might seem to move in the opposite direction, multiplying entities beyond what we can observe. Critics argue that multiverse theories risk becoming unfalsifiable, impossible to test through observation or experiment, and therefore outside the bounds of proper science. Defenders respond that the multiverse isn't proposed arbitrarily, but emerges naturally from our best physical theories when these are followed to their logical conclusions. If string theory or eternal inflation is correct for reasons we can test in our universe, then the multiverse they predict would be an unavoidable consequence, even if the other universes remain beyond our direct observation. The debate touches on fundamental questions about the nature and purpose of scientific theories. Is a theory valuable only if it makes predictions we can directly verify? Or is it sufficient for a theory to provide a coherent explanatory framework that accounts for what we can observe, even if it also implies the existence of things we cannot observe? These questions have no simple answers and continue to provoke lively debate among physicists and philosophers of science. Religious and spiritual perspectives on the multiverse vary widely. Some see it as a challenge to traditional theological concepts, particularly those centered on the uniqueness or special status of our universe. Others find in the multiverse concept an expansion of divine creative potential, or a scientific framework compatible with certain mystical traditions that have long spoken of multiple levels or dimensions of reality. The multiverse represents one of the most expansive reconceptualizations of reality in human intellectual history. It asks us to consider that everything we've ever observed or measured, our entire cosmic horizon, containing billions of galaxies, might be just an infinitesimal fraction of a much larger, perhaps infinite reality. It suggests that the Big Bang, rather than being the absolute beginning of everything, might have been just one birth event among countless others in an eternal creative process. As we continue our exploration of what might have existed before the Big Bang, we next turn to an even more fundamental question. How could anything, even a multiverse, emerge from true nothingness? This leads us to one of the most counterintuitive aspects of quantum physics, the concept that, at the quantum level, nothing is never truly nothing, and something can indeed come from nothing. We've journeyed across vast cosmic scales, contemplating cyclic universes and parallel realities, but now we approach perhaps the most profound question of all. Could our entire universe have emerged from nothing? The very idea seems to defy basic intuition. From nothing, nothing comes has been a foundational principle of philosophy since ancient times. And yet, modern quantum physics offers a startling possibility that under certain conditions something can indeed arise from nothing, and our universe may be the ultimate example of this extraordinary phenomenon. To understand how this might be possible, we need to explore one of the strangest aspects of quantum mechanics, the behavior of seemingly empty space. Classical physics viewed a vacuum as simply nothing, the absence of matter and energy, perfect emptiness. But quantum mechanics reveals a very different picture. At the smallest scales, empty space is anything but empty. It's a seething, bubbling quantum foam, where particles and energy fields flicker in and out of existence in a dance of perpetual creation and annihilation. These momentary appearances are known as quantum fluctuations, tiny, random variations in energy fields that briefly produce pairs of particles and antiparticles. These virtual particles appear spontaneously, exist for an incredibly brief moment, typically less than a trillionth of a second, and then reunite and annihilate each other, disappearing back into the quantum vacuum. This isn't just a theoretical concept. The effects of these virtual particles have been measured in laboratories through phenomena like the Casimir effect, where two uncharged metal plates placed extremely close together are pushed together by quantum fluctuations in the surrounding space. What makes these quantum fluctuations possible is Heisenberg's uncertainty principle, one of the cornerstones of quantum mechanics. This principle states that certain pairs of physical properties, like position and momentum, or energy and time, cannot be precisely measured simultaneously. The more accurately you know one property, the less accurately you can know the other. One implication of this principle is that the energy of a system can fluctuate spontaneously by a small amount, provided that these fluctuations last for only a very brief time. The greater the energy fluctuation, the shorter it must be. This opens a fascinating loophole in the conservation of energy. For extremely brief periods, energy can seemingly appear out of nowhere, manifesting as virtual particles before disappearing again. The quantum vacuum isn't truly nothing. It's a state of minimum energy that contains the potential for these fluctuations. But what if, under extraordinary circumstances, a quantum fluctuation didn't disappear? What if it somehow became stabilized and expanded into something much larger? This is precisely what some cosmologists propose might have happened at the Big Bang. According to this view, our entire universe might have begun as a quantum fluctuation, a random energy variation in a pre-existing quantum state that, instead of quickly disappearing, underwent a process of cosmic inflation, expanding exponentially to become the universe we observe today. But this immediately raises a deeper question. If our universe emerged from a quantum fluctuation, what was fluctuating? What was the quantum state that gave rise to our universe? Was it truly nothing, or was it some more fundamental reality with its own properties and laws? Some physicists, including Lawrence Krauss and the late Stephen Hawking, have argued that the universe could indeed arise from nothing in a meaningful sense. They suggest that the laws of quantum mechanics allow for the spontaneous creation of space, time, and matter from a state that contains no classical reality, no space, no time, no particles, nothing that we would recognize as something in everyday terms. In this view, even the laws of physics themselves could be an emergent property rather than something that pre-existed the universe. Just as the rules of chess emerge from the game being played rather than existing independently of it, the laws of nature might emerge along with the universe itself, rather than being imposed from outside. Others argue that this quantum nothing isn't truly nothing in the philosophical sense. It still assumes the existence of quantum fields, the laws governing them, and the mathematical structures that describe them. True nothingness, in the philosophical sense, would contain not even the potential for existence. No fields, no laws, no mathematics, no structure of any kind. Some critics argue that explaining the universe as a quantum fluctuation merely pushes the fundamental question back a step. Where did the quantum fields and laws come from? This debate touches on the limits of what science can meaningfully address. Science operates by developing models that explain observed phenomena and make testable predictions. But when we ask about the ultimate origin of existence itself, we may be approaching a boundary beyond which empirical science cannot go. Might be partially addressed by quantum mechanics, but its deepest implications may remain in the realm of philosophy and metaphysics. Nevertheless, the concept of quantum fluctuations provides a fascinating framework for thinking about cosmic origins. Let's explore more concrete aspects of how quantum processes might have given birth to our universe. One of the most developed theories in this area involves quantum tunneling, a phenomenon where particles can pass through energy barriers that would be impossible to traverse according to classical physics. In quantum mechanics, particles behave partly like waves, and these waves have a small probability of appearing on the other side of a barrier, even when the particle doesn't have enough energy to climb over it. It's as if you created a small bubble of space with properties different from its surroundings. If this bubble contained an energy field in an unstable state, like a ball perched at the top of a hill, it could then roll down towards stability, releasing energy that drove an exponential expansion of space through the process of cosmic inflation. Another approach comes from quantum cosmology, which attempts to apply quantum mechanics to the entire universe. In this framework, the universe as a whole has a quantum wave function that describes all possible configurations it might take. Just as an electron exists in a superposition of many possible states until observed, the entire universe might have existed in a superposition of many possible configurations before collapsing into a specific state that included a Big Bang and the subsequent evolution we observe. These models are mathematically intricate, with most requiring advanced concepts from quantum field theory and general relativity. One particularly influential approach is the no-boundary proposal, developed by Stephen Hawking and James Hartle in the 1980s. This model suggests that asking about the exact beginning of the universe is like asking about the edge of the Earth. There isn't one. Just as the Earth's surface is finite but has no boundary or edge, the universe's history might be finite in the past direction, but without a singular starting point or boundary. In the no-boundary proposal, the dimension of time gradually emerges from a state where all dimensions are space-like. This avoids the problem of an initial singularity with infinite density and temperature. Instead, the beginning of the universe is rounded off like the bottom of a bowl, with the early universe being a four-dimensional space, without a distinct time dimension. As the universe expands, one dimension gradually takes on the properties of time as we experience it. Another intriguing concept is the zero-energy universe hypothesis, which suggests that the total energy of the universe precisely equals zero. This might seem counterintuitive given the vast amounts of matter and energy we observe around us. However, the positive energy represented by matter, radiation, and even dark energy might be exactly balanced by the negative gravitational energy of the universe. Gravity, uniquely among fundamental forces, can be associated with negative energy, because bringing masses together through gravitational attraction releases energy rather than requiring it. When we add up all the positive and negative energy in the universe, the sum may be exactly zero, like a cosmic balance sheet that adds up perfectly. If the universe truly has zero net energy, then its creation wouldn't violate energy conservation, even from nothing. A universe with zero total energy is, in one sense, equivalent to no universe at all from an energetic perspective. This provides another avenue for understanding how quantum fluctuations might have produced our entire cosmos without violating fundamental physical principles. These theoretical frameworks remain speculative, with no clear way to definitively prove or disprove them through current observations. The most we can hope for is indirect evidence, finding that certain models make predictions about observable aspects of our universe that can be tested. For instance, different quantum origin scenarios might predict slightly different patterns in the cosmic microwave background radiation or in the distribution of galaxies across space. The challenge is substantial because any signature from the quantum origin of the universe would have been imprinted in the earliest moments of the Big Bang and then stretched and diluted by billions of years of cosmic expansion. Detecting such signatures requires extraordinarily precise measurements and careful analysis to distinguish the primordial signal from more recent effects. Additionally, many different theoretical models can make similar predictions about what we observe, making it difficult to definitively rule out alternative explanations. The field of quantum cosmology faces what philosophers of science call underdetermination, the situation where available evidence cannot discriminate between competing theories. Despite these challenges, the pursuit continues, driven by the profound importance of the questions involved. Understanding whether and how the universe could have arisen from quantum fluctuations touches on some of the most fundamental aspects of reality, the nature of space and time, the relationship between quantum mechanics and gravity, and the very meaning of existence. The notion that our vast cosmos, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, might have originated from a quantum fluctuation provides a humbling perspective. Does the quantum origin of the cosmos suggest a random, purposeless beginning, or might it reveal a deeper order embedded in the seemingly chaotic quantum realm? These questions have no simple answers, and different thinkers will draw different conclusions based on the same scientific models. Some see in quantum cosmology a universe that creates itself, requiring no external cause or creator. Others note that the quantum laws that might allow for such self-creation still represent a kind of order that itself requires explanation. Even if our universe arose from a quantum fluctuation, the fact that reality includes quantum fields that can fluctuate in this way might still prompt us to ask why reality has this character rather than some other. Quantum fluctuations also connect to another concept in modern physics that might help explain cosmic origins: vacuum energy, the energy inherent in apparently empty space. This mysterious energy pervades the universe and may have played a crucial role in both the birth of our cosmos and its continuing expansion. As we transition to exploring vacuum energy in more detail, we'll see how these quantum effects might work on a cosmic scale to create and shape entire universes. Imagine drifting through the void of deep space, far from any star or galaxy. To our human senses, this realm would appear completely empty, a perfect vacuum devoid of matter or energy. Yet modern physics tells us that this apparent emptiness is an illusion. Even the most perfect vacuum we could achieve, stripped of every particle of matter and every ray of light, would still contain something profound and mysterious: vacuum energy, a fundamental property of space itself. This concept represents one of the most revolutionary insights of modern physics. Empty space is never truly empty. At the quantum level, what looks like nothingness is actually a roiling sea of energy, where quantum fields permeate every point in space and particles pop in and out of existence in a never-ending dance. This vacuum energy, also called zero-point energy, persists even at absolute zero temperature, when all other forms of energy have been removed. It represents the lowest possible energy state of physical fields, their ground state. Yet this ground state is not zero, but a positive value. The existence of vacuum energy was first predicted in the early days of quantum mechanics and has since been confirmed through numerous laboratory experiments. One of the most famous demonstrations is the Casimir effect, where two uncharged metal plates placed extremely close together are pushed toward each other by quantum fluctuations in the surrounding space. This happens because the tiny gap between the plates restricts which wavelengths of virtual particles can exist there, creating a pressure difference that pushes the plates together. This measurable force arises purely from the properties of supposedly empty space, but the implications of vacuum energy extend far beyond laboratory curiosities. On the cosmic scale, vacuum energy may be responsible for the mysterious dark energy that appears to be accelerating the expansion of our universe. More profoundly, vacuum energy might hold the key to understanding how our universe came into being in the first place and what, if anything, existed before the Big Bang. To appreciate this possibility, we need to explore a concept known as false vacuum. In quantum field theory, fields can exist in different energy states, much like a ball on a hilly landscape might rest in various valleys or depressions. The lowest possible energy state is called the true vacuum, while higher energy states that appear stable but could eventually decay to a lower state are called false vacuums. Imagine a ball resting in a small depression on a hillside. It's stable for the moment, but not in the absolute lowest possible position. Given enough energy, or through quantum tunneling, the ball could escape this local minimum and roll down to a deeper valley. Similarly, a false vacuum state in quantum fields appears stable, but contains excess energy compared to the true vacuum state it could eventually decay into. Some cosmologists propose that our universe began when a pre-existing space in a false vacuum state underwent a phase transition to a lower energy state. This transition would have released an enormous amount of energy, driving a period of exponential expansion known as cosmic inflation. As this inflating region expanded, quantum fluctuations within it would have been stretched to cosmic scales, eventually giving rise to the temperature variations we observe in the cosmic microwave background and the large-scale structure of our universe. In this scenario, our Big Bang wasn't the absolute beginning, but rather a transition point, the moment when a pre-existing vacuum state changed configuration, releasing energy that formed our observable universe. The false vacuum that preceded our universe might itself have emerged from earlier transitions, potentially extending backward indefinitely or emerging from even more fundamental processes. This leads to a fascinating possibility known as eternal inflation. If the pre-existing false vacuum was expanding rapidly in a state capable of such fluctuations, vacuum energy provides a framework for understanding this state, not as absolute nothingness, but as a fundamental field permeating space, capable that could seed entire universes. But this raises an even deeper question. Where did the vacuum energy itself come from? What determined its properties? Why does a vacuum have the specific energy it does, rather than some other value or no energy at all? These questions push beyond current physics into speculative territory, but several approaches have emerged. One possibility is that vacuum energy is an inherent property of existence. There simply is no such thing as absolute nothingness in a physical sense. Perhaps what we perceive as nothing is actually a quantum field in its minimal state, and this minimal state necessarily contains some energy. The property is intrinsic to the thing itself. Another perspective comes from string theory, which suggests that the vacuum is filled with tiny vibrating strings, whose vibration patterns determine the fundamental particles and forces we observe. Different configurations of these strings would create different vacuum states with different energies. In the string theory landscape, with its vast number of possible configurations, our universe might occupy just one valley in an almost infinite dimensional terrain of possible vacuum states. The properties of our particular vacuum, including its energy density, would then be the result of which valley our cosmic dice happen to roll into. In this picture, vacuum energy isn't explained by a single fundamental principle, but is a contingent outcome of a vast landscape of possibilities, each realized somewhere in the multiverse. A third approach suggests that vacuum energy might be explained by deeper symmetries or constraints we haven't yet discovered. Perhaps the observed value of vacuum energy isn't arbitrary, but is necessarily connected to other fundamental constants or principles. Some unified theories attempt to derive vacuum energy from more basic principles, though none has yet provided a complete, verified explanation. The mystery deepens when we consider the measured value of vacuum energy in our universe. Quantum field theory calculations suggest that the vacuum energy density should be astronomically large, so large that it would tear apart atoms and prevent any structures from forming. Yet astronomical observations indicate that the actual vacuum energy, if it's responsible for dark energy, is extremely small, about 120 orders of magnitude smaller than theoretical predictions. This discrepancy, sometimes called the vacuum catastrophe or the cosmological constant problem, represents one of the greatest unsolved mysteries in physics. Why is the vacuum energy we observe so precisely tuned to allow for a universe with complex structures like galaxies, stars, and ultimately life? Some see this as evidence for a multiverse, where different regions have different vacuum energies, and we necessarily find ourselves in a region compatible with our existence. Others search for unknown physical principles that might naturally explain the observed value. Beyond these theoretical considerations, how might vacuum energy relate to what existed before the Big Bang? Several scenarios have been proposed. In the eternal inflation model mentioned earlier, our universe emerged from a pre-existing inflating false vacuum. This metastable state might have persisted indefinitely into the past, with no absolute beginning but rather an eternal process of bubble universe creation. Alternatively, vacuum energy might undergo cycles of increasing and decreasing value, corresponding to expanding and contracting phases of a cyclic universe. The vacuum energy would oscillate between different states, driving the cosmic cycles. A third possibility involves vacuum energy fluctuations in a more fundamental quantum gravitational state. In this scenario, space and time themselves emerge from quantum fluctuations in a pre-existing state that isn't quite a physical vacuum as we understand it, but something more fundamental, perhaps a network of quantum relationships or a foam of microscopic wormholes. These theoretical frameworks remain highly speculative, operating at the boundaries of known physics. Directly testing ideas about vacuum energy in pre-Big Bang conditions presents immense challenges, as our observational window is limited by the cosmic horizon. We can only directly observe events that have had time to send light signals to Earth within the age of the universe. Scientists are exploring indirect methods of investigating these questions. One approach involves precise measurements of the cosmic microwave background radiation, looking for patterns that might reveal the nature of the vacuum state that preceded our observable universe. Another involves particle physics experiments that probe the behavior of quantum fields under extreme conditions, potentially shedding light on how vacuum energy behaves and transitions between states. Advances in theoretical physics also continue to refine our understanding of vacuum energy. Concepts from quantum information theory, holographic principles, and other cutting-edge areas are being applied to the problem of cosmic origins, seeking more robust mathematical frameworks for describing how universes might emerge from vacuum states. The philosophical implications of vacuum energy are as profound as the physical ones. If our universe emerged from a quantum vacuum state through natural processes governed by physical laws, what does this tell us about cosmic purpose or design? Some see in vacuum energy a purely materialistic explanation for existence. Universes arise naturally from the inherent properties of quantum fields, requiring no external cause or creator. Others note that this merely shifts the question: why do quantum fields have precisely the properties that allow for universe creation? Why does the vacuum have any energy at all? Why do physical laws exist and take the specific form they do? These deeper questions might point beyond physics to metaphysical considerations about the nature of reality itself. If even empty space contains energy and virtual particles, perhaps absolute nothingness is a philosophical concept that has no corresponding physical reality. What we call nothing in physics always turns out to be something, a quantum field in its lowest energy state, but still a field with structure and properties. This insight resonates with ancient philosophical traditions that questioned whether pure non-existence is even a coherent concept. As the Greek philosopher Parmenides argued over 2,000 years ago, perhaps nothing cannot be. True nothingness may be a logical impossibility rather than a physical state that could have preceded our universe. As we contemplate these profound questions, we might find a certain poetic beauty in the vacuum energy concept. The seemingly empty space all around us turns out to contain the seeds of creation, a sea of possibilities from which entire universes might emerge. Far from being barren nothingness, the vacuum represents infinite potential, a canvas on which the cosmos paints its grand structures through quantum principles. This perspective connects scientific inquiry with more spiritual or philosophical views of cosmic origins. Many religious and mythological traditions speak of creation emerging from a primordial state that transcends ordinary understanding. Whether it's the formless void in Genesis, the quantum vacuum of modern physics, or the concept of sunyata, emptiness that is full of potential, in Buddhist philosophy. Though the languages and frameworks differ greatly, there's a common recognition that what preceded our visible universe wasn't simple non-existence, but rather a more fundamental state from which existence as we know it emerged. The scientific concept of vacuum energy gives this ancient intuition a precise mathematical form, though it leaves many profound questions still to be answered. As we conclude our exploration of vacuum energy, we transition to considering how various religious and philosophical traditions throughout human history have grappled with the question of cosmic origins. These diverse perspectives remind us that the quest to understand what came before the Big Bang isn't just a scientific endeavor, but a deeply human one, touching on our most fundamental questions about existence, meaning, and our place in the cosmos. Long before telescopes peered into deep space or particle accelerators probed the quantum realm, humans gazed at the stars and wondered about cosmic origins. Across cultures and throughout history, our ancestors crafted rich narratives to explain how existence began. These ancient cosmologies, expressed through myth, religion, and philosophy, represent humanity's first attempts to answer the profound question: what existed before the universe as we know it? While modern science offers unprecedented insights based on observation and mathematics, these earlier perspectives remain culturally significant and philosophically profound. They remind us that the question of cosmic origins isn't merely scientific, but touches on our deepest existential concerns about meaning, purpose, and our place in the grand scheme of reality. By exploring these diverse traditions alongside scientific models, we gain a more complete understanding of how humans have grappled with the mystery of beginnings. Many religious cosmologies begin with an eternal, uncreated deity who brings the universe into being. In the Abrahamic traditions, Judaism, Christianity, and Islam, God exists outside of time and space, creating the cosmos ex nihilo from absolute nothingness. This simple yet profound declaration suggests that before creation, there was only God, eternal, unchanging, and completely sufficient unto himself. This concept of creation from nothing differs significantly from scientific models of quantum fluctuations or vacuum energy, which describe processes occurring within a pre-existing framework of natural laws. The theological claim is more radical. Not just matter and energy, but the very laws of nature themselves were brought into existence by divine will. Nothing physical pre-existed creation, only the transcendent reality of God. Yet even within these theological traditions, different interpretations have emerged. Some religious thinkers embrace a more literal reading of creation narratives, seeing God as directly fashioning the universe in sequential acts over specific time periods. Others interpret these texts metaphorically, viewing them as conveying spiritual truths rather than scientific descriptions. Some contemporary theologians find compatibility between religious creation accounts and scientific cosmology, seeing the Big Bang as the mechanism through which divine creative power operated. Eastern religious traditions often present a different perspective on cosmic origins. In Hindu cosmology, the universe undergoes endless cycles of creation, preservation, and dissolution. Rather than a single beginning, this view posits a beginningless sequence of universes, each lasting billions of years. The Rig Veda, one of humanity's oldest religious texts, contemplates the mystery of what came before. Who really knows? Who will hear proclaim it? Whence was it produced? Whence is this creation? The gods came afterwards, with the creation of this universe. This cyclic conception bears intriguing parallels to scientific models of oscillating universes. Both envision cosmic history as rhythmic rather than linear, with each universe emerging from the remains of its predecessor. The difference lies in the timescales involved and the causal mechanisms proposed. Buddha famously declined to answer certain metaphysical questions, including those about the ultimate beginning of things. This reluctance stemmed not from ignorance, but from the belief that such speculations did not contribute to spiritual liberation. This pragmatic stance resonates with certain philosophical positions in Western thought, which question whether the concept of an absolute beginning is even coherent. If every event requires a prior cause, how could there be a first event? If time itself had a beginning, what could it mean for something to exist before time? These puzzles have challenged philosophers for millennia. Ancient Greek thinkers developed sophisticated approaches to these questions. Aristotle argued for an eternal, uncreated universe, finding the concept of absolute beginning philosophically problematic. If nothing existed before the universe, what could have caused it to come into being at one moment rather than another? Without prior conditions to differentiate one moment from another, there seemed no reason for creation to occur at any particular time. Plato, in his dialogue Timaeus, proposed that the universe was fashioned by a divine craftsman, the demiurge, who imposed order on pre-existing chaotic matter. This view differs from creation ex nihilo, suggesting instead a transformation of eternal, formless substance into the ordered cosmos we observe. The demiurge works not from nothing but from primordial materials, guided by eternal forms or patterns. This concept of a pre-existing substance taking on structure parallels certain scientific descriptions of symmetry breaking in the early universe, where uniform fields differentiate into distinct forces and particles. Both accounts describe a transition from undifferentiated potentiality to specific actualities, though through very different mechanisms. Other ancient cultures developed equally rich cosmogonies. In Chinese tradition, the universe emerges from undifferentiated chaos, Hundun, through the interplay of complementary forces, yin and yang. Egyptian mythology describes creation arising from Nun, the primordial watery abyss. Norse legends tell of the void Ginnunga Gap, where fire and ice interact to begin the cosmic process. Across cultures, we find recurring motifs, formless potential giving rise to structured reality, often through the interaction of opposite principles. These ancient myths weren't primitive science, but served different functions, providing cultural identity, moral guidance, and a sense of cosmic order. Yet they often contain profound philosophical insights that resonate with contemporary questions. When quantum physics describes particles emerging from vacuum fluctuations, or when cosmologists ponder inflation fields transitioning from false to true vacuum states, they're exploring similar boundary conditions between non-being and being that ancient myths addressed through different language. The philosophical concept of the first cause represents another approach to cosmic origins. Developed most famously by Thomas Aquinas in the 13th century, This argument reasons backward from the chain of causes we observe in the universe. Since every effect has a cause, and that cause is itself the effect of a prior cause, there must ultimately be an uncaused first cause. Otherwise, we face an infinite regress of causes with no beginning. This first cause, which Aquinas identified with God, exists necessarily rather than contingently. Unlike everything else in the universe, which could have been otherwise or not existed at all, the first cause contains the reason for its existence within itself. It doesn't begin to exist, but exists eternally and necessarily, providing the ultimate ground for all contingent reality. Some modern cosmological theories might seem to eliminate the need for a first cause. Eternal inflation or cyclic universe models push the beginning indefinitely into the past, apparently avoiding the need for an absolute starting point. Yet philosophers point out that these models still assume certain laws and conditions, quantum fields with specific properties, for instance, without explaining why these exist rather than nothing, or why they have the particular characteristics they do. The contemporary philosopher of religion William Lane Craig has refined the first cause argument into what he calls the Callum cosmological argument, which draws on both philosophical reasoning and modern cosmology. Craig argues that whatever begins to exist must have a cause. The universe began to exist, as evidenced by the Big Bang and the impossibility of an actually infinite past. Therefore, the universe has a cause. This cause must be timeless, spaceless, and immensely powerful, attributes traditionally associated with God. Critics respond that quantum mechanics shows some events don't require deterministic causes, or that the concept of causation may not apply before time began. Others suggest that physical laws themselves might be the necessary foundation from which contingent reality emerges, without requiring a personified first cause. Beyond questions of primordial causes, philosophical traditions have explored how we should conceptualize time itself. Augustine of Hippo, in his Confessions, argued that time is part of creation rather than a framework within which creation occurs. God made time itself, he wrote. For Augustine, asking what God was doing before creation is meaningless because there was no before. Time itself began with creation. This perspective aligns remarkably with Einstein's understanding of time as an aspect of spacetime, beginning with the Big Bang rather than providing an eternal backdrop. Both views challenge our intuitive notion of time as an absolute, endless flow, suggesting instead that temporality itself might be contingent rather than necessary. Contemporary philosopher Quentin Smith takes a different approach, arguing that the universe might be logically prior to its own existence, essentially self-causing. In his view, the laws of quantum mechanics could allow the universe to create itself in a causal loop that transcends ordinary temporal sequence. While highly speculative, such proposals illustrate how philosophical thinking continues to evolve alongside scientific developments. The diverse perspectives we've explored remind us that the question of cosmic origins operates at the intersection of empirical investigation, logical reasoning, and existential concern. Science provides our most powerful tools for understanding the mechanisms through which the universe has evolved, but philosophical and religious traditions often address the why questions that extend beyond empirical methods. These different approaches need not conflict. Many scientists find inspiration in religious or philosophical worldviews while maintaining rigorous scientific standards in their work. Conversely, many religious believers embrace scientific discoveries as revealing the mechanisms through which divine creativity or natural principles operate. The question of what existed before the Big Bang remains open to multiple levels of explanation. Perhaps the most profound insight from this survey of perspectives is the recognition of mystery at the heart of existence. Whether through the language of quantum fields or divine transcendence, we approach boundaries where our ordinary concepts and categories become insufficient. The origin of all things may ultimately transcend full human comprehension, not because of temporary gaps in our knowledge, but because of the inherent limitations of minds evolved within the universe, trying to grasp the conditions of the universe's own possibility. This doesn't mean we should stop asking the question. The wonder and curiosity that drive us to peer beyond the Big Bang connect us with our ancestors who told stories of cosmic eggs and primordial waters. The question of beginnings seems woven into human consciousness itself, perhaps because in contemplating cosmic origins, we're also exploring our own nature and purpose. As we look toward future discoveries that may shed new light on these ancient questions, we carry forward this legacy of wonder. The next generation of telescopes, particle accelerators, and theoretical frameworks may reveal aspects of cosmic history currently hidden from view. Yet even as our knowledge expands, the mystery of existence itself, the question of why there is something rather than nothing, will likely continue to invite diverse perspectives from science, philosophy, and spiritual traditions alike. As we've journeyed through the various theories about what might have existed before the Big Bang, we've encountered the limits of current human knowledge. We've explored cyclic universes, quantum fluctuations, vacuum energy, multiverses, and ancient philosophical perspectives, but science never stands still. Even as you listen to these words, researchers around the world are developing new tools, theories, and experiments that may one day pull back the cosmic curtain further than ever before, revealing more about our universe's earliest moments, and perhaps even what came before. What might these future discoveries look like? What technologies and theoretical breakthroughs could transform our understanding of cosmic origins in the coming decades? Let's explore the frontiers where answers might emerge. Our ability to peer back toward the beginning depends largely on the sensitivity of our observational tools. The James Webb Space Telescope, launched in December 2021, represents a quantum leap in our capacity to observe the early universe. With its unprecedented infrared sensitivity, Webb can detect light from the first galaxies that formed after the Big Bang, showing us the universe as it appeared just a few 100 million years after its birth. While this doesn't directly reveal what came before the Big Bang, understanding the earliest structures helps constrain cosmological models and test predictions about initial conditions. The next generation of telescopes will push these boundaries even further. Ground-based behemoths like the extremely large telescope, ELT, in Chile, with its 39-meter primary mirror, will collect 13 times more light than today's largest optical telescopes. This increased light-gathering power will allow astronomers to see fainter, more distant objects, potentially revealing details about how the first stars and galaxies emerged from primordial gas clouds. Radio astronomy is experiencing its own revolution, with facilities like the Square Kilometre Array, SKA, an international effort to build the world's largest radio telescope across Africa and Australia. When completed, the SKA will map the distribution of hydrogen throughout cosmic history, potentially detecting signals from the cosmic dawn, the era when the first stars illuminated the universe and began reionizing the neutral hydrogen that pervaded space after the Big Bang. These observatories won't directly show us what existed before the Big Bang, but they'll provide crucial constraints on theoretical models. By revealing the detailed structure of the early universe, they'll help eliminate theories that don't match observations and strengthen those that correctly predict what we see. They'll push our empirical knowledge closer to the beginning, narrowing the gap between what we can observe and what we must infer through theory. Perhaps the most promising avenue for investigating the pre-Big Bang era comes from gravitational wave astronomy, a field that didn't exist in practical terms until 2015, when the Laser Interferometer Gravitational Wave Observatory, LIGO, made the first direct detection of gravitational waves from merging black holes. Unlike electromagnetic radiation, which cannot reach us from before the cosmic microwave background, when the universe became transparent about 380,000 years after the Big Bang, gravitational waves could potentially carry information from much earlier epochs. Future gravitational wave observatories, like the Laser Interferometer Space Antenna, LISA, planned for launch in the 2030s, will be sensitive to lower frequency gravitational waves than current detectors. This could allow them to detect echoes from inflation, the theorized period of exponential expansion in the first fraction of a second after the Big Bang. If inflation theories are correct, it would have generated a background of primordial gravitational waves that still permeate the universe today. Detecting these primordial gravitational waves would not only confirm inflation, but potentially reveal details about the inflationary process itself, how long it lasted, how energetic it was, and whether it followed the patterns predicted by various theoretical models. This information could help discriminate between different scenarios for what might have preceded inflation, including various multiverse models, bounce cosmologies, or pre-inflation quantum states. Even more speculative is the possibility that gravitational waves might carry information from before the Big Bang itself. Some cyclic universe models predict that gravitational waves from a previous cosmic cycle could, in principle, pass through the bounce into our current universe. While detecting such signals would be extraordinarily challenging, requiring technologies well beyond our current capabilities, they're not forbidden by known physics. Future generations of gravitational wave observatories, perhaps utilizing quantum measurement techniques we can barely imagine today, might someday detect these whispers from a previous cosmic epoch. Beyond observational astronomy, particle physics offers another window into cosmic origins. The Large Hadron Collider, LHC, at CERN has already revolutionized our understanding of fundamental particles by confirming the existence of the Higgs boson. Future particle accelerators with even higher energies, like the proposed Future Circular Collider, FCC, or Compact Linear Collider, CLEC, could probe energy regimes closer to those that existed in the earliest moments after the Big Bang. While even these advanced accelerators can't recreate the extreme energies of the Big Bang itself, they can test predictions made by theories about the fundamental structure of reality. Discovering new particles or confirming theories like supersymmetry would provide crucial insights into the basic building blocks of our universe and the laws governing their interactions. This knowledge, in turn, would constrain models of how our universe began and what might have existed before. Theoretical physics will likely undergo its own revolutions in coming decades. Currently, our two most successful physical theories, quantum mechanics and general relativity, don't fully integrate with each other. Quantum mechanics excels at describing the subatomic realm, while general relativity brilliantly explains gravity and the large-scale structure of space-time. But at extreme conditions like those of the Big Bang or within black holes, both theories are needed simultaneously, and they don't play well together. Developing a complete theory of quantum gravity, a framework that seamlessly unites these approaches, represents the holy grail of theoretical physics. Candidate theories like string theory, loop quantum gravity, causal set theory, and asymptotic safety each offer potential pathways, but none has yet been definitively confirmed by observation. Breakthroughs in quantum gravity could transform our understanding of the Big Bang singularity and potentially reveal what physical processes might have preceded it. These theoretical advances may come from unexpected directions. History shows that revolutionary insights often emerge from seemingly unrelated areas of research or from reconceptualizing existing problems. For instance, insights from condensed matter physics have sometimes illuminated questions in cosmology. The development of new mathematical tools or computational methods might suddenly make tractable problems that previously seemed impenetrable. Artificial intelligence and machine learning are already transforming how scientists analyze astronomical data and simulate complex physical systems. As these tools grow more sophisticated, they might help identify subtle patterns in observational data that human researchers would miss, or explore vast parameter spaces of theoretical models more efficiently than conventional approaches. While AI won't replace human creativity in developing fundamental theories, it could accelerate progress by handling computational heavy lifting and suggesting promising avenues for investigation. Quantum computing represents another technological frontier with potential implications for cosmological research. Quantum computers leverage the principles of quantum mechanics to perform certain calculations that would be practically impossible for classical computers. As these systems mature, they could enable more sophisticated simulations of quantum fields in the early universe, or more efficient analyses of astronomical datasets, potentially revealing new insights into cosmic origins. Laboratory experiments probing exotic states of matter might also illuminate cosmic processes. For example, researchers have created quark-gluon plasmas, a state of matter that existed microseconds after the Big Bang by colliding heavy ions. Future experiments might create analogues of other extreme conditions relevant to cosmic origins, allowing scientists to test theoretical predictions in controlled settings. Another promising approach involves searching for subtle traces the pre-Big Bang era might have left in the cosmic microwave background radiation, CMB. This afterglow of the Big Bang has already provided crucial evidence supporting the standard cosmological model. More sensitive measurements of the CMB's polarization patterns could potentially reveal signatures of gravitational waves from inflation or even from earlier epochs. Projects like the Simons Observatory and potential future space missions dedicated to CMB polarization might detect these elusive signals. The distribution of galaxies throughout space also contains information about cosmic origins. Next-generation galaxy surveys like those from the Vera C. Rubin Observatory or the European Space Agency's Euclid mission will map billions of galaxies across cosmic time. The statistical properties of this distribution, how galaxies cluster on different scales, depend on the initial conditions established in the earliest moments of the universe, potentially providing clues about pre-Big Bang physics. Beyond these planned initiatives, entirely new observational windows might open unexpectedly. Few astronomers in 1950 would have predicted that we would one day detect gravitational waves or directly image black holes. Similarly, future generations might develop entirely new ways of probing the cosmos that we cannot currently foresee. Perhaps detecting cosmic neutrinos from the first second after the Big Bang, or developing methods to observe dark matter directly, or discovering new messengers entirely. Particles or fields we haven't yet identified that carry information across cosmic distances. While these technological and theoretical developments offer exciting possibilities, we should acknowledge the potential limits of empirical investigation. Some aspects of what existed before the Big Bang may remain permanently beyond observational reach. If our universe began in a true singularity that erased all information about previous states, or if pre-Big Bang physics operated according to principles utterly different from those we can test, direct empirical confirmation might be impossible. Yet even in the face of such limits, scientific progress continues through indirect evidence and theoretical consistency. Theories about pre-Big Bang conditions can make predictions about observable consequences in our current universe. Those that make successful predictions gain credibility, while those that don't are modified or discarded. Through this iterative process, science gradually narrows the range of plausible explanations, even for phenomena not directly observable. The coming decades will likely bring surprises that reshape our understanding in ways we cannot anticipate. The history of cosmology teaches humility. Many confident assertions about the universe have later been overturned by new evidence or theoretical insights. The steady-state theory, once a serious competitor to the Big Bang model, was eventually abandoned as evidence for cosmic evolution accumulated. Similarly, some of our current ideas about what came before the Big Bang may one day seem naive or incomplete in light of future discoveries. This uncertainty shouldn't discourage us, but rather inspire wonder at the ongoing adventure of cosmic exploration. Each generation of scientists builds upon the achievements of those who came before, gradually extending humanity's understanding further into the cosmic past. The question of what existed before the Big Bang, once considered purely metaphysical or religious, has become accessible to scientific investigation through this cumulative process of discovery and theoretical development. As we look toward this future of exploration, we're reminded that the greatest scientific breakthroughs often come from combining multiple approaches: theoretical insight with observational evidence, technological innovation with conceptual creativity. The ultimate answers about cosmic origins will likely emerge not from a single definitive experiment, but from converging lines of evidence across astronomy, physics, mathematics, and perhaps fields we haven't yet imagined. The search for what existed before the Big Bang represents science at its most ambitious, reaching beyond the known, stretching our minds to encompass realities larger than ourselves, and refusing to accept that any question is permanently unanswerable. This quest connects us with our ancestors who gazed at the stars and wondered where everything came from, while employing tools of unprecedented precision and theoretical sophistication. It's a journey that continues to unfold, page by page, discovery by discovery, as humanity writes the ongoing story of cosmic understanding. We began our journey with a simple yet profound question: what existed before the Big Bang? As we've explored various scientific theories, philosophical concepts, and religious perspectives, we've ventured to the very edge of human knowledge, that misty frontier where established understanding fades into speculation and speculation into mystery. The quest to understand cosmic origins reveals as much about ourselves as it does about the universe. Our drive to push beyond the boundaries of the known speaks to something fundamental in human nature. Throughout history, our conception of the universe has continuously expanded, from a flat Earth beneath a dome of stars, to a solar system, to a galaxy, to billions of galaxies stretching across billions of light years. The theories we've explored about what might have existed before the Big Bang, cyclic universes, multiverses, quantum fluctuations, vacuum energy, represent the latest expansion of our cosmic horizon. These theories remain speculative, existing at the frontier where physics merges with philosophy. The Big Bang represents a boundary to our empirical knowledge, a cosmic horizon beyond which direct observation becomes extraordinarily difficult, if not impossible. Yet the absence of certainty doesn't diminish the value of the quest. Each theory offers a different perspective on reality, a different way of conceptualizing the unobservable past. Together, they form a constellation of possibilities, illuminating different aspects of the cosmic mystery, while acknowledging that the full truth may transcend our current understanding. Perhaps what's most remarkable is that we can ask these questions at all. We are collections of atoms arranged into conscious beings, products of the very universe we're trying to understand. Our brains evolved to help our ancestors survive, not to contemplate quantum cosmology. Yet through mathematics, observation, and theoretical creativity, we've managed to extend our understanding far beyond our biological origins. The quest to understand what existed before the Big Bang unites science, philosophy, and spirituality in a common pursuit. While their methods and languages differ, all seek to penetrate the mystery of origins, to connect our limited human perspective with something larger and more fundamental. The wisest approach is one of intellectual humility, combined with boundless curiosity, acknowledging the limitations of our current understanding while continuing to push those boundaries outward. Our current theoretical frameworks, impressive as they are, will likely seem incomplete to future generations, just as Newtonian physics seemed complete until Einstein's revelations. The question of what existed before the Big Bang also invites us to reconsider the nature of time itself. Our everyday experience of time as a linear flow from past to future shapes how we think about causality and origins. But both relativity and quantum mechanics suggest that this intuitive conception may be incomplete. Time may be more flexible, more relative, or more emergent than our common sense suggests. The beginning of our universe may also represent the beginning of time as we understand it, making the concept of before problematic in a literal sense. The mystery of cosmic origins invites a sense of wonder that unites us across cultural and historical divides. When we gaze up at the night sky, we participate in an experience shared by countless generations before us. The experience of awe before the vastness and beauty of the cosmos, coupled with the burning desire to comprehend our place within it. The atoms in your body, the carbon, oxygen, nitrogen, and other elements that form your physical being, were created through nuclear fusion in stars that lived and died long before our solar system formed. In a very real sense, the universe has evolved the capacity to contemplate itself through us. We are the means by which the cosmos has become conscious of its own existence and history. As we conclude our exploration, we return to the sense of mystery with which we began. The question of what existed before the Big Bang remains open, with multiple plausible theories but no definitive answer. Yet this very openness is an invitation to curiosity, to wonder, to continued exploration. The mystery doesn't diminish in value because it remains unsolved. Rather, it gains significance as a driving force for human inquiry and creativity. In embracing this mystery, we connect with something essential in the human spirit, the desire to understand reality in its fullest sense, to see beyond appearances to underlying truths, to comprehend our place in the cosmic story. The question of what existed before the Big Bang may never receive a final, definitive answer. But in asking it, in exploring possible responses, in stretching our minds to contemplate realities beyond everyday experience, we participate in one of humanity's noblest endeavors, the quest to understand the cosmos and our place within it.